بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف خلق الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. إن شاء الله نبدأ سلسلة جديدة وهي تحمل عمق الموضوع، وهي الستاندر موديل، و يعني به مسمى سميت عنوان السلسلة التي تخصني نظريات على اليوتيوب تشرح تفسر الستاندر موديل أو مقارنة نظريتي بالستاندر موديل. فكل تلك الفيديوهات هي مقدمة لهذه السلسلة. سلسلة مكونة من 12 فيديو يقدمها المحاضر دومينيك، أستاذ رائع جدا جدا، كلام مفهوم وشرحه عميق وتدريسه أيضا عميق. في هذه السلسلة سنتناول الستاندر موديل QED ستاندر موديل، طبعا ليس فيها QCD، هذا ما اكتشفته أخيرا، لأنه كنت أتمنى أن أجد محاضرات إضافية عن QCD. الستاندر موديل لا يحتاج لQCD، بالرغم من أنه يتحدث عن الكواركات. طبعا خرجنا من السلسلة السابقة، أو مثلا لحد الآن درسنا 3 سلسلتين. السلسلة الأولى كوانتم ميكانيك، الجزء الأول الثاني أو 1B، هو ده مدته 27 فيديو، مقدار 27 فيديو شرحنا فيه شرح كامل. بعد ذلك انتقلنا لسلسلة كوانتم ميكانيكس 2، أيضا قدمنا فيها شرح تمام. هذه السلسلة الثالثة اللي هو الستاندر موديل. في السلاسل السابقة طلعنا معلومات غاية في الأهمية، السلسلة الأولى خرجنا بمعلومات عن تصرف الكتلة وطريقة الكوانتيزيشن وطريقة ما تسمى بالكونسترينت. السلسلة الثانية ربما آخر محاضرات رأيتموها، طلعنا بهذا عدم التناظر وهذه المفارقة بين المجال الكهربائي والمجال المغناطيسي في QCD، وفي حتى في الإلكترويك أيضا سنحاول نطبق هذا الأمر، بحيث أنه داخل الكتل تكون الغلبة والانتصار للمجال المغناطيسي، وخارج الكتل في الفضاء المطلق تكون الغلبة والانتصار للمجال الكهربائي. طبعا هذه طبعا تقريبا يعني ليس دقيقا. لماذا؟ لأن الانتقال ليس انتقالا فجائيا، إنما الانتقال متدرج حسب معادلة المترية تعالوسي، يعني ممكن نشوفها حسب هذه المترية. الانتقال هو انتقال مفترض يكون انتقال سلس من الحد الأول للحد الثاني، الحد الأول بالموجب والحد الثاني بالسالب. الانتقال يكون انتقال سلس، وبالتالي يجب أن يكون الانتقال بين المجال الكهربائي للمجال المغناطيسي انتقال سلس. فخارج الطاقة الكثيفة، خارج الفضاء الكثيف، خارج الكتل، يعتبر المجال الكهربائي هو السيد، والمجال المغناطيسي هو الأقل، وهذا ظاهر في السبين، وظاهر في أنه الإلكترونات والبروتونات تتفاعل عن طريق المجال الكهربائي. السبين نحتاج إلى طاقة نجعله واضحا وظاهرا، نحتاج إلى طاقة. داخل الفضاء الكثيف أو داخل الكتل نجد أنه العكس صحيح، أن المجال المغناطيسي هو المسيطر والمجال الكهربائي هو ضعيف. وذلك فسرنا بهذا الأمر، فسرنا الظاهرة الغريبة التي جعلت باي بايون هي الكتل الفعالة والكتل الحاملة للطاقة أو القوة، وأن شريكتها الأساسية التي تسمى سيجما تم تنحيتها تماما، وحتى العلماء لم يستطيعوا تفسير ذلك، لكن الحمد لله فسرناه خلال هذا الأمر أنه المجال الكهربائي في داخل النواة وداخل البروتون والنيوترون وداخل الجسيمات الأولية عموما، نجد أن المجال الكهربائي دوره يمحى ويسيطر المجال المغناطيسي، وبالتالي نستطيع أن نفسر أن القوى النووية القوية والقوى النووية الضعيفة هي عبارة عن مجالات مغناطيسية، ليست فقط طاقة كهرومغناطيسية وإنما مجالات مغناطيسية. والقوى النووية الضعيفة ربما تلعب فيه الجاذبية دورا ولو بسيطا، لأنه لديه خواص جاذبية، لأنه الكتل متقاربة، خاصة أيضا في الQCD نجد أن القوى النووية القوية كتل متقاربة، البروتون متقارب جدا من النيوترون، وبالتالي تلعب فيه جاذبية أيضا. لكن في الإلكترويك اللي هي القوى النووية الضعيفة نجد أن المسافات 10 أس ناقص 18 داخل البروتون داخل النيكلون، 10 أس ناقص 18 هي مسافة صغيرة جدا تلعب فيه الجاذبية دورا كبيرا شوية. الجاذبية والمغناطيس يعني تتفقان مع بعض ولا تختلفان مع بعض، مثل كتاب الحلقة 54 و55 أن استعنتوا بالمعادلة التي تكافئ معادلة التكافؤ بين السترينجز فيلد وبين ريمان تنسر، وبالتالي الخواص المغناطيسية والخواص الجاذبية الجسيمات هي متقاربة من بعضها البعض، تظهر ذلك في الQCD والQED أقصد الإلكترويك. هذا ما فعلناه في السلسلتين السابقتين. في هذه السلسلة تعال نكتشف ماذا يحدث، سنطبق نفس المفاهيم في السلاسل السابقة في هذه السلسلة. تعال نشوف ماذا يحدث وبماذا نستطيع أن نخرج في هذه السلسلة.
Okay, welcome to this second part of the Standard Model Theory lecture. In the first part of this semester you discussed QCD and renormalization, and in the second half of the semester we will mainly focus on the electroweak standard model, sometimes generalized to general electroweak theory, possibly even beyond the standard model, but mainly we will discuss the structure.
طبعا ذكر الإلكترويك، إذا نحن ما دام ذكر الإلكترويك فنحن سنكون ملتزمين بالنظرية التي أو الفرضية التي تقول أن مجالات المغناطيسية هي المسيطرة. سنبحث عن المجال المغناطيسي بين قوانين ومعادلات الإلكترويك، وأيضا نبحث عن الجاذبية. بالمناسبة الجاذبية مهمة جدا في الإلكترويك، لأنه نحن نتكلم عن 10 أس ناقص 18، ومع هذا مع 10 ناقص 18 نحن موجودين داخل البروتون وداخل النيوترون، يعني أبعاد صغيرة وداخل كتلة. وانظر إلى كتلة البروتون وكتلة النيوترون مثلا أو الجسيمات الأولية عموما، هذه الكتلة تكبر وتتضخم مع نقصان الأبعاد. كلما نقص الأبعاد كلما تضخمت الكتلة وتضخمت الطاقة أيضا. لهذا نجد التفاعلات عالية الطاقة تظهر في عند الأبعاد الصغيرة، تظهر هذه الطاقة عالية جدا جدا لكي تتفوق على الطاقة المطلوبة، طاقة الفضاء ثنائي الأبعاد التي هي 10 أس موجب 123. يعني انظر إلى هذه الأبعاد، عند هذه الأبعاد الصغيرة الفضاء ثنائي الأبعاد لديه طاقة 10 أس 123، مفترض أن تتغلب عليها طاقة التفاعل اللي هي بالتيرا إلكترون فولت. تيرا إلكترون فولت أو أقل جيجا إلكترون فولت بالنسبة للمفاعلات المصادمات الجزيئات. فالجيجا إلكترون فولت مفترض أن تتغلب على طاقة قدرها 10 أس موجب 123. وتفسير ذلك هو أن عند الأبعاد الصغيرة الطاقات تتضخم، يعني الجيجا تكون أكثر من ذلك، تصل إلى حتى إلى 120 جول. يعني تفسير معادلة الطاقة هي 120 جول، 110 أس 120 جول، وليس إلكترون فولت وليس جول، وعلى متر، وليس جول فقط، على متر. يعني لكل متر 10 أس 123 جول أو 120 جول. إذا تفوقت هذه الطاقة على 10 أس 123 تحصل التفاعلات المادية مباشرة ويتم طرد الكتل من التفاعل. إذن هنا علينا نكتشف شيئا جديدا بالإضافة ما اكتشفناه سابقا، على أنه عند الأبعاد الصغيرة هذه خواص المغناطيسية تسيطر، خواص الجاذبية تسيطر. سنبحث هذا الأمر داخل القوانين وداخل المعادلات التي يصيغها هذا البروفيسور. طيب تعالوا نشوف هذا الموضوع.
Of the electroweak standard model itself. Okay, so let me give you an outline of what we plan to do. The topic is the electroweak standard model, and the goals are in particular that I want you to get a thorough understanding of the structure of the standard model, like which parts of the standard model, which aspects of its definition lead to which particular consequences, so that you also see how modifications of the standard model in the gauge sector or in the Higgs sector or in the fermion sector would influence different observables. And we want to discuss the standard model extensively at tree-level, first of all, because as you have also seen in other lectures, a tree-level understanding is often almost identical to an all orders understanding, because tree-level discussions can often be repeated on the level of Slavnov-Taylor identities for the full theory, and then the tree-level structure repeats itself in the exact theory, and then consequences derived at tree-level can also be understood at the all-order level. So tree-level will be discussed extensively, and then we will discuss also the renormalization of the electroweak standard model in detail, which is a difficult and complex topic, and so we will devote some time to it, and then we will also apply it and discuss certain interesting one-loop physics examples of the electroweak standard model. Okay, so let me start with the first chapter of this, which is a tree-level discussion. And we will first focus on one generation only. And the second section of the lecture will then be tree-level with 3 generations, where we discuss the specifics of having 3 generations of fermions. Okay, and so I will begin with a brief phenomenological discussion of the phenomenological basis, like what are the phenomena which we know, which must be described by the standard model. Then we will give the construction of the standard model Lagrangian. This is for sure known to most of you or even all of you, but we obviously need to repeat it in order to establish the notation. Then we will study the spontaneous symmetry breaking and the Higgs mechanism in detail. We will also discuss the BRST formalism in order to understand the physical and unphysical degrees of freedom in the theory. And then we do an application or phenomenological discussion of property of the standard model, which is very influential for electroweak physics, namely the so-called custodial symmetry. That is a property, I would call it one of the miracles of the standard model, and there will be actually several of those miracles which we discuss, but the custodial symmetry is especially important. So we discuss it here in detail, and at the end, of course, we will summarize this section by giving the Feynman rules for the tree-level standard model. Okay, so let us discuss the phenomenological basis. So the first kind of phenomenological basis, in other words, the first kind of observations that we have done in order to enforce the standard model description is, of course, we have discovered a lot of particles, namely which particles exist. We know all the quarks, all the leptons, and the various gauge bosons. So I just write it here as a list because obviously you know which particles there are. So there are left-handed neutrinos, left-handed electrons, right-handed electrons. Description is, of course, we have discovered a lot of particles, namely which particles exist. We know all the quarks, all the leptons, and the various gauge bosons. So I just write it here as a list because obviously you know which particles there are. So there are left-handed neutrinos, left-handed electrons, right-handed electrons, left-handed up quarks, left-handed down quarks, right-handed up quarks, right-handed down quarks, and there are the photon, W plus minus Z gauge bosons, and there is also the Higgs boson. All these particles exist, they have all been observed, and they have certain properties, masses and spin, and I do not write down all those properties because you know them anyway, but all, let's just summarize, all these have been observed, and the masses, spins, and other quantum numbers have been determined, and they are in agreement with the predictions of the standard model. So I do not write it down. So obviously these are spin 1/2 fermions, these are spin 1 vector bosons, this is a spin 0 Higgs boson with certain gauge quantum numbers, electric charges, and so on. The next kind of phenomena which was observed is phenomena at low energies. So that goes back to, let's say, the beginning of elementary particle physics, for example, in the 1940s, 1950s, 1960s, where the first particle accelerators have been constructed, which operated at energies maybe around 1 GeV or below 1 GeV, such that one could not produce directly particles like the WZ boson or the Higgs, but one could study processes between the light particles, namely the first generation fermions, and look at decays of mesons, interactions between mesons and baryons, and so on. And there are two kinds of phenomena which I want to highlight. The first one is QED. So of course we know about QED processes, and QED had been established as the correct description of low energy phenomena involving the electromagnetic interaction. That is established, for example, in atomic physics, in chemistry, molecular physics, condensed matter physics. All of that relies on QED. So QED is established as the correct description of low energy processes involving only electromagnetic interactions. So consequences of QED are, as I said, atomic physics, chemistry, and or classical electrodynamics, and many more, and all of that had been established. But it was discovered that the electromagnetic interaction is not the only interaction which acts between elementary particles. As you know, there is also the strong interaction, which we neglect today. But in addition, there is the weak interaction. The weak interaction generates or mediates physical processes which cannot be mediated by QED, but which have different incoming and outgoing states. And how was the weak interaction observed at low energies? For example, by radioactive decays, by beta decay and by decays of baryons and mesons, and also by the muon, but the muon is not a first generation particle. But by such decays, one could observe the weak interactions. So, let's say beta decay, muon decay. I nevertheless include muon decay because of its importance, but there are also other weak decays, for example, pion decay. And many more such interactions. They were observed, and they cannot be described by QED because here the so-called flavor changes. An up quark is transformed into a down quark, or an electron is transformed into a neutrino, and the electromagnetic interaction never changes this so-called flavor of particles. Therefore, these flavor-changing interactions must have corresponded to interaction which goes beyond QED, the so-called weak interaction.
أريد أن أضيف معلومة هنا أن الفليفر تعبر عنها بالمجالات المغناطيسية. هذه الفليفرز، والمجالات المغناطيسية هي التغيرات في المجالات المغناطيسية بالنسبة للمكان والزمان. الزمان يمكن أن يكون ثابتا لأن الأبعاد هي ثابتة، أبعاد صغيرة، وبالتالي لدينا معدلات تدفق زمان عالية، لكن المكان يتغير، وتغير المكان هو يعطينا نوع من الديجريز اوف فريدوم، لأننا نتكلم الآن عن محاور كارتيزية اكس واي زد، لا نتحدث عن محاور قطبية، وبالتالي هذه تعطينا نوع من الديجريز اوف فريدوم. 3 أنواع من الديجريز اوف فريدوم، ربما تزيد وربما تصبح أكثر من 3، يمكن تصبح 6، لأنه الزمان يمكن أن نعتبره يتغير في هذا الموضوع أيضا، لأن الزمان والمكان عبارة عن دوائر حول الجسيم، يكون شكل دوائر حول الجسيم. إذا بما أنه في دوائر، إذا نحن نتعامل معه، مفترض نتعامل معه في محاور قطبية، لكن ما دام استخدمنا المحاور الكارتيزية فإن الزمان والمكان أيضا يتغيران. فمشتقة المجال المغناطيسي بالنسبة للزمان والمكان راجعوا كتاب الحلقة 54 و 55، كما تراجعوا هذه السلسلة الحلقات الأخيرة من السلسلة السابقة اللي هو كوانتم QFT2 أو كوانتم فيلد 2. ما أريد أن أقوله هنا أن نعم التغير في المجال المغناطيسي بالنسبة للتغير في الزمان والمكان يكون عاليا جدا، وحتى المجال المغناطيسي يعطينا نوع من الاستغلالية ليست كاملة، لأنه نجد أن الكواركات تتفاعل، الجلونات تتفاعل بجلون وأنتي جلون أو كلر وأنتي كلر، وبالتالي كأنما ألغت بعضها البعض. وبالتالي الديجريز اوف فريدوم 3 كلرز هذه هي عبارة عن الكلر، هي عبارة عن الفضاء في الثلاثي الأبعاد، طول عرض ارتفاع، لكن هنا يدخل فيه المجال المغناطيسي. المجال المغناطيسي في الفضاء الثلاث أبعاد، طول عرض ارتفاع، لكن ليس مجال مغناطيسي فقط، إنما المجال المغناطيسي مشتقة المجال المغناطيسي بالنسبة للزمن وبالنسبة للفضاء. إذا تغير الفضاء يعطينا تغير لهذا المجال المغناطيسي، سنتأكد من هذه المعلومة إن شاء الله من خلال هذه السلسلة.
And by observing this, one could determine properties of the weak interactions. And so let me just write down something. So these decays, for example, muon decay was observed to be compatible with the following Feynman diagram. You have an incoming muon, an outgoing muon neutrino. You have here a W minus boson, and in the final state you have an electron and an anti-neutrino. And in this Feynman diagram, you must assume that this vertex here and also the other vertex is proportional to coupling constant, let's call it GW, times gamma mu, times the left-handed projection operator 1 minus gamma 5 over 2. And the W boson propagator that you must assume in order to get agreement with you must assume that this vertex here and also the other vertex is proportional to coupling constant, let's call it GW, times gamma mu, times the left-handed projection operator 1 minus gamma 5 over 2. And the W boson propagator that you must assume in order to get agreement with the observation is that you can simply say in the numerator you have G mu nu, and in the denominator you have Q square minus a mass mW square, where the Q square here can be neglected. So, and therefore the whole discussion of the whole Feynman diagram is in the end proportional to 2 powers of the coupling constant squared divided by 2 powers of the mass mW square, and everything else are constants like gamma matrices, metric tensor, and so on. So the entire prediction of this diagram is proportional to this combination. So what is the non-trivial fact about this? The non-trivial fact is first of all that you have here this gamma mu times left-handed projector interaction at both vertices. This gives rise to a particular angular behavior of the decay products and a certain dependence on the chiralities of the incoming and outgoing fermions. And this particular dependence was in agreement with observation, and all other possibilities like 1 plus gamma 5 or no gamma mu, just the unit matrix here, and so on, all of those alternatives are not compatible with observation. So by testing all possibilities here, one determined that this is the correct necessary structure. And the other ingredient is that in the propagator you can approximate this propagator here by a constant 1 over mW square. And then it tells you that you are not discovering the existence of a W boson here in this way. This is just a Feynman diagram which numerically agrees with your observation, and the only numerical value you can extract from experiment is the combination here between the coupling constant and the mass mW square, and the fact that there is this left-handed coupling. Okay, so this was the status of the observation at low energies. Then there are obviously a phenomena.
طبعا هنا ظهرت الجاما 5. الجاما 5 في المحاضرة في السلسلة السابقة المحاضرة الأخيرة ظهرت فقط في الكيو سي دي، درسناها كان في الكوانتم ميكانيك 1 بي أظن، وكوانتم ميكانيك 2 السلسلة الأخيرة، ولم تظهر معنا ثاني إلا في الكيو سي دي. إذن سنعمل حساب إلى أن الجاما 5 تعبر عن هذه المجالات المغناطيسية. كيف؟ الله أعلم، لكن جاما 5 تعبر عن المجالات المغناطيسية، وهذه معلومة جديدة، وهي تتكون من 4 أنواع من الجاما. جاما 0 مضروبة في جاما 1 مضروبة في جاما 2 مضروبة في جاما 3. هذه هي جاما 5. ما الذي يجعل جاما 5 تكون عبارة عن مضروب ل4 أنواع من الجامات؟ جاما 0 هي الايدنتيتي. الجاما 1 لها علاقة بمعادلات بباول ماتريكس، يعني ربما تكون في اتجاه هيكس مثلا. الجاما 2 تكون في اتجاه واي. الجاما 3 تكون في اتجاه زد. كلها مضروبة بعض حتى تعطينا جاما 5. وهذه الجاما 5 لها علاقة بالمجال المغناطيسي. هذا ما سنحاول نثبته إن شاء الله بإذن الله تعالى. السبب الذي ذكر أنه هذه الثوابت كلها not compatible with experiment الشيء بسيط جدا وسهل جدا جدا، وهو عندما نقيس هذه التفاعلات نقيسها في وجود المجال الكهربائي، وهي حصلت أصلا في وجود أو في نقول تمييز المجال المغناطيسي، لأنه حصلت داخل الميون وحصل الانحلال داخل الميون، وأعطانا هذه وجود المجال المغناطيسي، تمييز للمجال المغناطيسي، ونحصل نحصل لها في التمييز بالنسبة للمجال الكهربائي. هنا يحصل اختلافات، سنرى ذلك إن شاء الله.
At higher energies, and they are available not since the 1950s, but maybe since the 1970s, 80s, 90s, and currently. And there we have in particular so-called electroweak precision observables. They are of particular relevance, and but they are not, of course, the only observables which are measured at high energies. But let us focus on them. And so the first observation here is the discovery of the W and Z bosons, and after their discovery, we have a direct measurement of MW and MC, and we can define an abbreviation of the ratio of the two. Namely, let's define MW divided by MZ is equal to CW, which is 1 minus SW squared. So in particular, you can, of course, determine the individual masses, but as a corollary, you can also determine the mass ratio, which is a dimensionless number, CW, which is therefore also an important observable of the Standard Model. And just to let you know, I will introduce, this is of course an abbreviation of the so-called weak mixing angle, cosine theta, but I will now introduce at least 5 different cosine theta. They will all differ by the indices. So I call that CW, not theta or theta W or whatever. Let me just check whether this can be seen on the camera. So this is the first kind of important observables, and the next.
طبعا في الطاقات العالية تختلف في الطاقات المنخفضة. الآن WZ ظهرت في الطاقات العالية، ظهرت بسبب أن الفضاء ثنائي الأبعاد يقوم بطرد الكتل. في الطاقات المنخفضة أيضا الفضاء ثنائي الأبعاد يقوم بطرد الكتل، لكن في الطاقات العالية الفضاء ثنائي الأبعاد يقوم بطرد الكتل بطريقة قوية جدا جدا. بالتالي هذه الطريقة القوية ربما هي التي أظهرت WZ، والWZ طبعا لا تظهر في شكل بارتيكلز، إنما تظهر في شكل معادلات رياضية ربما تدخل فيها الجاما 5، وهذا يخبرنا عن المجال المغناطيسي ظهر في هذا الأمر، ظهر بقوة. والسنارة ذاته نوع التفاعل الكيميائي، التفاعل دون ذري. السنارة نوعه لأنه التفاعل إذا كان طاقته عالية البروبيجاتور يكون عالي كبير، وبالتالي يحصل الخواص المغناطيسية تكون موزعة على مكان كبير، يعني ليس فيه داخل البروتون فقط النيكلون الميون فقط، إنما يتوزع في فضاء كبير، وبالتالي ربما تظهر هذه الخاصية خارج الفضاء. ربما ذلك لا نعلم، لكن نحن محتاجين أن نعرف نوع التفاعل وكيف يسير هذا التفاعل وكيف نقيس من ذلك التفاعل، لأن هناك كسر عشوائي للطاقة أو للميون، كسر عشوائي. هذا الكسر العشوائي يحمل الجسيمات الخارج من التفاعل ومعها بعض الخواص المغناطيسية. ربما تم قياس هذه الخواص المغناطيسية وهي التي سببها أظهرت الدبليو والزي. هناك كثير من الاحتمالات، لكن تعال نشوف.
Kind of important precision observable is the structure of interactions. So we can look at effective interactions of vector bosons with spin 1. So after the observation of photon W and Z boson interactions with two fermions. So, and the blob means that I am talking not about the Feynman rule, but about the effective measured interaction strength between the three particles here in question. And this effective interaction strength can be defined somehow experimentally and also somehow in theory, and it will depend on the momenta of So this is the first kind of important observables, and the next kind of important precision observable is the structure of interactions. So we can look at effective interactions of vector bosons with spin 1. So after the observation of photon W and Z boson interactions with two fermions. So, and the blob means that I am talking not about the Feynman rule, but about the effective measured interaction strength between the three particles here in question. And this effective interaction strength can be defined somehow experimentally and also somehow in theory. And it will depend on the momenta of all the three particles and so on. So it might be a complicated thing and certainly not just a number, but it is very similar to Feynman rule. So in theory, the three-level contribution to this would be the three-level Feynman rule, but then there would be higher order corrections as well. Okay, but let's denote the observed interactions in this way. Photon with two fermions. And approximately what one finds is the following: minus I E Q F times gamma mu. So I write the interactions in a way such that they can be directly compared with ordinary Feynman rules. And then what you see here is the ordinary QED Feynman rule for this interaction. And we observe that for all energies, this is approximately equal to that structure with a certain charge quantum number specific to each fermion. And this becomes exact at low energies by definition of the charge E. So the unit of charge or the gauge coupling of QED is defined, at least in one particular definition scheme, so-called on-shell renormalization scheme. It is defined to be exactly the measured interaction strength between the photon and fermions at low energies. Then W, here some fermion F prime, and here another fermion F. So if you similarly look at the W fermion interaction strength at some momenta, then it can be written as follows: minus I E divided by square root of 2 times S theta W gamma mu times a left-handed projectile. Do you all know what the PL symbol means? Has it been defined already? Okay, it's of course this thing here. I don't know whether it has been defined already in this lecture. 1 minus gamma 5 over 2. So, and now you see here the basic point is that the gamma structure of the interaction has the form gamma mu times a left-handed projectile. That is the observation. And then there is a numerical prefactor in front of this gamma structure. And this numerical prefactor is just some number, but I can write any number as the previously defined electric charge divided by some mu symbol S theta W. And now I introduce a second S theta W, which might be different or the same as that one over there. So this is just a completely general ansatz for a general numerical prefactor in front of the left-handed structure. And of course,
طبعا في الطاقات العليا ظهرت الكيرالتي left handed و right handed، وهذا ما يعطينا به المجال المغناطيسي، وظهرت الجاما 5 مرة أخرى. فركزوا على الجاما 5 وركزوا على الكيرالتي، لأنه الجاما 5 هي تعبر عن الكيرالتي، وركزوا على أنه مجال مغناطيسي، وركزوا على الدبليو ثيتا هذه أو الاس دبليو ثيتا، ربما تكون زاوية، وبالتالي يعطينا الهاي انرجي، يعطينا زوايا معينة، زوايا معينة هذه تحدد المجالات المغناطيسية، وسنكتشف ذلك.
The measurements tell you that the gamma structure is the one which is seen experimentally, and then you can determine the value of that number by measuring of the left-handed structure. And of course, the measurements tell you that the gamma structure is the one which is seen experimentally, and then you can determine the value of that number by measuring. Next, Z boson interaction with one fermion can be approximately written as follows: minus I E divided by 2 S theta Z S C theta Z times now the following gamma mu. And here we have the following gamma structure. We have a gamma mu and then different numerical prefactors in front of the 1 and in front of the gamma 5. Namely, we have I3F minus 2QF sine square theta effective F minus I3F times gamma 5, where the I3F is equal to the T3 weak of the left-handed part of the fermion. So we will see that later, but you know, of course, that those particle multiplets that I wrote here correspond to the field content of the electroweak standard model. There are left-handed fermion doublets, right-handed fermion singlets, and the left-handed fermion doublets have a so-called isospin, weak isospin quantum number. The upper doublet component has isospin plus 1/2, the lower component has isospin minus 1/2. That applies only to the left-handed fermions, and the I3F is the abbreviation for any fermion for that weak isospin of the fermion's left-handed part. So for an electron, the I3F would be, for example, -1/2. For a neutrino, this I3F would be +1/2, and so on. Okay. And then you see here the following structure, which is again observed experimentally. Namely, you have a gamma mu structure where gamma mu is multiplied with some linear combination of the unit matrix and gamma 5. And you can, of course, without loss of generality, write the coefficient in front of gamma 5 with this I3F, which is a fixed, basically integer or half integer number. And then the numerical coefficient of this is determined by that prefactor here. And that prefactor, I made an ansatz, the previously defined E, divided by some new symbols S theta Z, C theta Z. So new mixing angles corresponding to the Z boson interactions. So this is a completely general ansatz, and that number would be determined by measuring the gamma 5 part of this structure here. And then for the unit matrix part, I make a new ansatz, and then this number is already measured. So if you measure the unit matrix, you determine in this way the sine square theta effective for the respective fermion. Okay. So it's also a completely general ansatz for the unit matrix, and experimentally by measuring gamma 5 you determine this, and by measuring the unit matrix you determine that. So we have now two more weak mixing angles, namely the mixing angle S theta Z and the mixing angle sine theta effective for the respective fermion. So for each fermion there is of course a different such sine square theta effective, because that relative prefactor might depend on the nature of the fermion. And this is observed, it's approximately true for any momentum, and by definition this becomes exact if the momenta are on the Z pole. So if the Z boson is on shell, like in a process where you do E plus E minus going to Z boson, and the E plus E minus energy is exactly such that you can produce a Z boson at rest, then the Z boson decays into two fermions. Then, by definition, this becomes exact, and so then you have an exact measurement description to determine this weak mixing angle here. This is in the jargon, this is simply called at the Z pole, where you produce the Z boson basically on shell. So these are three very important effective interactions, and so I basically gave you now the measurement prescription to determine E, S theta W, S theta Z, sine theta effective. Now one more, namely muon decay. So muon decay is approximately described by this Feynman diagram, but let's say exactly you do muon going to electron, electron antineutrino, and muon neutrino. And similarly you define an effective interaction strength for this, and let's give it a name in a certain convention for the normalization. This is called the muon decay constant, G mu, or Fermi constant. And that again can be defined to be equal to the following structure, namely E squared divided by 4 square root of 2 times mw square times c sine theta mu square. And then you have a measurement prescription, measure muon decay, that determines unambiguously the value of this muon decay constant. So by definition, you set the muon decay constant equal to that ratio here. E square is already determined, m square is determined, so that effectively determines the measurement prescription for S theta mu. Okay, then you have done all those measurements.
طبعا لاحظوا التعقيدات في الطاقة العالية والطاقة المنخفضة، وهذا واضح أن مجالات المغناطيسية تلعب دورا في الطاقة العالية، تلعب دورا كبيرا في الطاقة العالية. الطاقة المنخفضة لا تلعب دورا كبيرا فيها. وهذا ناتج على أنه كلما زادت الطاقة كلما نقصت أبعاد التفاعل، وكلما زادت عند الأبعاد الصغيرة تزيد الخواص المغناطيسية، القوة المغناطيسية تزيد، لأن القوة المغناطيسية عبارة عن مشتقة البي بالنسبة لمشتقة المكان ومشتقة الزمان. عندنا كلما نقصت الأبعاد كلما زادت الطاقة نقصت الأبعاد، كلما نقصت الأبعاد زادت خواص الطاقة القوة المغناطيسية، وبالتالي تظهر خصائصها شيئا في التفاعلات عالية الطاقة.
And what is then the observation? The observation is that up to very small numerical effects or small numerical differences, all these weak mixing angles that I have introduced, which are defined by observations, are almost equal. So let's first say in general, all these depend on momenta, etc. But approximately we get SW, which was determined from the mass ratio MW over MZ, is approximately equal to S theta W, which was determined by the W boson interaction, approximately equal to S theta Z, which was determined in the gamma 5 part of the Z interaction, approximately equal to sine theta effective for the respective fermion, which is determined in the 1 part of the Z boson interaction, and that is also approximately equal to S theta mu determined in the muon decay. And that is obviously a fundamental and highly non-trivial observational fact which must be described by theory. And now, having said all that, okay, let me write it down. This is what must be described by theory. So having said all that, let me add that I introduced all those symbols here for pedagogical purposes. Not all of those symbols are used in the professional literature. So let me highlight the ones which are really used in the literature. I introduced all the other ones in order to make clear how non-trivial this relationship is and how many quantities are actually related by it. So the important quantities in the literature are this effective weak mixing angle, S theta effective, and the weak mixing angle defined via the masses. And later on there will be yet another weak mixing angle, which is the one defined in terms of the gauge couplings, which is the one that directly comes out of the structure of the theory. So this is all just pure experiment, but then there is also a natural definition within the theory, which is again different from all of that. Okay, but those are the important ones in the literature. And so let me just say the following. Example. The ratio between sine square theta effective, if you average over all the leptons, divided by this SW coming out of the mass ratio, this is often denoted as 1 plus delta kappa lepton. So this delta kappa stands for exactly this ratio. and this is numerically determined as follows. Namely, in the numerator we have 0.2315 and so on. In the denominator we have 0.2226 and so on. So you see here a few percent difference. Not a very large difference, but also not a tiny difference. It's a noticeable difference of a few percent. Similarly, if you do SW square from the mass ratio divided by S theta mu coming from mu on decay, then you get the following. This is defined as 1 plus delta R, and that is 1 plus 0.0354 and so on. So I underline again the quantity which is actually commonly used in the literature. That is the so-called quantity delta R. So instead of introducing the symbol that I introduced, S theta mu, one would introduce the symbol delta R in the literature, which is defined exactly in this way using our notation. And then the delta R is the shift between the two mixing angles, and it is a 3%. So again, not completely tiny, but small. I hope you know that the precision that has been reached in experiment is way, way higher than 3%. The precision is 10 to the minus 4, 10 to the minus 5 in many cases. Therefore, in terms of the precision that we have, this is a huge effect, and we must do very precise calculations in theory in order to check whether our theory actually agrees with this observation. Okay, so this ends our discussion of the observational basis. Theory must describe this, and we can say the following about the standard model. The standard model, particularly the electroweak standard model, is the simplest renormalizable quantum field theory, which is in agreement with all these observations. And now a little bit of history. Of course, today, when we have this list of observations, we have observed all the particles, including the Higgs, the W, and the Z boson, and we have measured very precisely all the interactions of all gauge bosons with all fermions. It is not such a big deal to guess the theoretical structure of the standard model. And however, this statement here, that the standard model is the simplest quantum field theory which agrees with observations, that was already the case before the W, Z, and the Higgs were discovered. Already there, you could ask yourself, what are the quantum field theories which describe, for example, that muon decay, and you only knew the ratio GW square over MW square, you had not seen the W boson, but already at that point, the standard model was the simplest renormalizable quantum field theory in agreement with all observations, but it was extremely hard to guess the structure of the standard model. And therefore, of course, Weinberg, Lesher, and Salam were awarded the Nobel Prize to come up with the structure of the electroweak standard model. And because it was the simplest quantum field theory in agreement with observation, and because the standard model contains the W-Z boson and the Higgs boson, we had predictions. We had predictions that all these bosons must exist with very precisely predicted properties. And all those predicted properties and the existence of the particles were, of course, confirmed later on. That was, of course, a triumph for theory and also for experiment. But we have now all the knowledge from these observations.
طبعا لاحظوا كلمة simplest model to describe the experiment أو simplest standard model. يعني الهياكل الرئيسية للستاندرد موديل صحيحة، لكن بعد ذلك علينا أن نضع بعض الحدود الإضافية التي تعتبر تغيرات طفيفة. هذه الحدود التي سميت بهذا الاسم Simplest Standard Model، لأن الاكسبيرمنت تختلف، والاختلاف ناتج من ماذا؟ ناتج من طاقة التفاعل ومن الخواص المغناطيسية. أنا مصر على أنه موضوع الخواص المغناطيسية. لماذا؟ لأنه نحن الآن نتكلم عن تفاعلات داخل الإلكترويك، يعني داخل الجزيء، داخل الجسيمات. طيب إذا لدينا خواص مغناطيسية ولدينا مجال جاذبي أيضا، لدينا مجال جاذبي أيضا ناتج من الكيرفتشر داخل هذه الجسيمات، فلدينا مجال جاذبي أيضا. لكن المجال الجاذبي ربما يظهر في شيء ما، لكن المجال المغناطيسي يظهر كثيرا لأنه هو متغير في الأبعاد الثلاثة. المجال الجاذبي لا أعتقد، ربما يكون متغير أيضا في الأبعاد الثلاثة بالمناسبة، لكن هذا احتمال ضعيف. لكن المجال المغناطيسي يتغير. لماذا أنا أربط دائما المجال المغناطيسي؟ لأنه نوع التفاعل قد يكون راسا لراسا، يعني هيد تو هيد، وقد يكون تفاعل جانبي، يعني التصادم ذاته الكوليجن قد يكون راسا في راس ويكون جانبي. كل هذا يعطينا زوايا مختلفة ويعطينا هذه المتغيرات، لأنه إذا كان التفاعل جانبي ليس راس براس، يعني في محور إكس ليس في محور إكس واي. إكس واي لدينا مجال جاذبي معين، إكس لدينا مجال جاذبي معين، واي مجال جاذبي معين، وهكذا. هذا ما يحدث هذه المفارقات البسيطة.
Therefore, our task is much simpler. So let us therefore come to the construction of the standard model Lagrangian. And actually, it is not quite right to say that the standard model is defined by its Lagrangian. It's better to say that the standard model is described by its symmetry content, and in particular by its gauge invariance and by its field content. And therefore we start by gauge invariance and fields. So the first thing is we have four vector bosons which were observed in the electroweak sector, namely photon W plus minus and Z. And if you know the structure of gauge theories, then you know that for each generator of the gauge group there is an associated gauge boson which becomes a vector boson particle. Therefore, we need a gauge group with 4 generators. And we know that the W boson has electric charge. Therefore, the W boson must interact with a photon. So we have self-interactions between the gauge bosons, like W plus, W minus, gamma, and some others. Therefore, we know that the gauge group must be non-abelian, because in an abelian gauge group there are no self-interactions between the gauge bosons. So the simplest gauge group which can appear, which can be in agreement with all these observations, must be a gauge group with exactly 4 generators. More than 4 would be not the simplest one. So 4 generators, but non-abelian, and the simplest example of this, or the only example, is SU2 cross U1. Therefore, our gauge group for the electroweak sector is SU2 left cross U1 for the so-called hypercharge. And let me nevertheless add in brackets here SU3 color times that, to have here in front of us the full gauge group of the entire standard model, but this is the electroweak sector with 1 gauge factor with 3 generators, the 3 Pauli matrices, for example, and an abelian group with 1 generator. Overall, we have 4 generators and a non-abelian gauge group. Having fixed the gauge group, we can immediately write down the general form of the gauge covariant derivative. Capital D mu is equal to the ordinary derivative plus, in my convention, I times the sum of the products of generators times gauge bosons. And here we must have generators and gauge bosons separately for each factor of the gauge group. Let me again also insert here QCD, even though we will afterwards neglect it. So maybe in brackets, the QCD part would be a gauge coupling GS times generators TSA times gluon fields GA mu, where this color index A runs from 1 to 8 for the 8 generators of SU3. Then for the electroweak part, we have GW times TA WA mu, where this A is the weak isospin index. A runs from 1 to 3. And then we have a part corresponding to the so-called hypercharge Y, namely the gauge coupling GY times the hypercharge generator capital Y times the corresponding gauge field B mu. That is the structure of the covariant derivative. So we have here the 4 so-called generators of the gauge group T1, 2, 3 and Y, and the 4 gauge fields, namely WA, mu and B mu. Now let me fix immediately one interpretation such that you have a gauge coupling GY times the hypercharge generator capital Y times the corresponding gauge field B mu. That is the structure of the covariant derivative. So we have here the 4 so-called generators of the gauge group T1, 2, 3 and Y, and the 4 gauge fields, namely WA, mu and B mu. Now let me fix immediately.
طيب في شيء أنا خطر ببالي الآن. تفسير قوة لورنز هي عبارة عن احفظ معي هذا التفسير، عبارة عن الشحنة مضروبة في المجال الكهربائي زائد الشحنة مضروبة في السرعة مضروبة ضرب اتجاهي في المجال المغناطيسي. تمام. إذن هناك اختلاف في السيمتري بين في قوة لورنز بين المجال الكهربائي والمجال المغناطيسي. المجال الكهربائي نجد مباشرة الشحنة مضروبة في المجال الكهربائي مباشرة، لكن في المجال المغناطيسي يختلف. هناك سرعة، والسرعة عبارة عن متغير إضافي مضروب في الحد الثاني. طيب داخل الكتلة تختلف الأبعاد. تعال نشوف. داخل الكتلة تختلف الأبعاد. نحن الآن نتكلم عن مجال مغناطيسي، نتكلم عن السرعة مضروبة في المجال المغناطيسي. فداخل الكتلة تختلف الأبعاد، أن الدي آر على الدي تي لا يكون يساوي السي، ربما يكون الحد الأول الذي هو بالموجب، وربما يكون الحد الثاني. وما دام نتكلم داخل الكتلة يكون هناك تنافس بين الحدين. طبعا الحد الثاني لا يظهر إلا في الثقب الأسود، لكن أقصد ليس ظهورا فقط، إنما أقصد أقصد يسيطر على المعادلة في الثقب الأسود. وحتى في الثقب الأسود ليس في الثقب الأسود مباشرة تحت أفق الحدث، لا. الثقب الأسود نعم نعم تحت أفق الحدث، لأنه M موجودة هنا في المعام. في ال EW نجد أيضا أن هناك تنافس بين الحدين. طيب هذه هي ما يتعلق بالسرعة، تتعلق بالتدريج المكاني على التدريج الزماني، وممكن نعتبرها هذا التدريج تؤثر جدا في السرعة. بما أنها تؤثر جدا في السرعة فإنها تؤثر جدا في هذه المعادلة. تعال نرجع مرة أخرى. تؤثر بدرجة كبيرة في هذه المعادلة. طيب من أي ناحية تؤثر في المعادلة؟ تؤثر في الكوبلينج. التي عبارة عن ماتريس، إذا كانت يونت ماتريس ليس لدينا فيها كلام. تؤثر في الدبليو، تؤثر في الجي واي كوبلينج واي، تؤثر في البي اللي هو الفيلد، تؤثر في الواي الهايبر تشارج، أيضا تؤثر في الواي، تؤثر في الهايبر تشارج. إذن علينا ندخل في رؤوسنا اختلافات المجال المغناطيسي في نسبة لأبعاد الثلاثة. 1. 2. دخول السرعة والتي تعبر عن التدريج المكاني على التدريج الزماني. ولاحظ في هذه المعادلة شيء ما، كلما زادت الكتلة، طبعا الكتلة ممكن نعبر عنها بالطاقة، الكتلة تساوي الطاقة على سرعة ضوء تربيع، يمكن نعبر عن ذلك. يعني المعادلة الأولى بدل الكتلة نضع E تربيع، والسي بدل ما تكون سي أس 6 ستكون سي أس 10، والحد الثاني سيكون E على سي تربيع أي سي أس 4. وبالتالي يمكن نعوض عن المعادلة بالطاقة، لا شرطا، يعني ليس هناك شرطا إلا الكتلة. يمكن نعوض بالطاقة، ويمكن نعوض بالشحنة بالمناسبة برضو. نعوض بالشحنة، بدل M ناخد Q الشحنة، وبدل G ناخد K اللي هو ثابت كولوم. فهذه المعادلة تشتغل فيهم كلهم. طيب وأريد أن أقوله هو شيء ما في غاية الأهمية، عن الفرق بين R و دي R و دي تي تتحكم فيه الكتلة. كلما زادت الكتلة كلما تقاربت دي R من دي تي، وهذه التقارب يجب أن نضعه في الاعتبار حتى نعرف هذه الفروقات ونصفها بالتدفق، معدلات تدفق المكان والزمان. يجب أن نأخذ هذه في الاعتبار. السبب الذي يجعلنا نقول ذلك لأنه نحن ذكر المحاضر أنه هذه المعادلة تجريبية أكثر، وبالتالي لو معظم الثوابت التي توضع تجريبيا يجب أن يكون لديها تفسير فيزيائي. التفسير الفيزيائي ليس لدينا طريقة نصفها إلا عن طريق المجال المغناطيسي، ليس المجال الكهربائي. لهذا نجد أن الكتلة الشحنة تتغير في الكواركات، لكن في الميون لا تتغير، الشحنة محفوظة، لكن تتغير في الكواركات اللي هو داخل البروتون، بحيث أن الشحنة تكسر. لماذا؟ لأن الأبعاد أقل، أبعاد أقل، هذا يعني الدي آر على دي تي أصبحت أقل، وبالتالي ربما السرعة في قوة لورنز، السرعة زادت في قوة لورنز، لأن عندما تقل المسافة، تفاضل المسافة إلى الزمن، هذه لما عندما تقل يصب ذلك في مصلحة زيادة السرعة. زيادة السرعة يمكن أن يقصد مباشرة من التشارج الواي، وبالتالي تقل التشارج. إذا نحن محتاجين نعرف ما هي التي والواي، ونعرف البي والدبليو كيف تمثل في الفضاء، أو كيف تمثل في معادلات، شكل معادلات.
interpretation such that you can imagine something for hypercharge. Certainly you know it already, but the interpretation is that we relate these generators to the electric charge of particles or fields Q as T3 plus the hypercharge Y. So this relationship will be justified later on. But let's write it down already here such that you can interpret something or have an understanding of where the values of the hypercharge come from. They always come from this relationship. By inverting this relationship, you can determine what must be the hypercharge of all the different fields in the theory. So whether this interpretation is actually possible and can be kept consistently in the discussion of the whole theory, we might not know that yet, but it will be possible. And so let's fix this already now. So in this way,
هناك شيء أيضا نسيت أن أقوله في غاية الأهمية. الدي ميو كابيتال دي ميو يعتبر مشتقة في الفضاء الكثيف، والدي ميو سمول دي ميو تعتبر مشتقة في الفضاء العادي اللي هو فضاءنا نحن، وبالتالي المشتقة في الفضاء الكثيف يساوي نفس المشتقة في الفضاء العالي، بالإضافة إلى هذه المتغيرات. كل هذه المعادلة كلها تعتبر متغيرات تؤثر في المشتقة في الفضاء العادي. إذن ما يحدث كالآتي: أن المشتقة في الفضاء الكثيف كلما زادت عمق التفاعلات أو زادت طاقة التفاعلات، هذه المعادلة التي تعتبر زائد المشتقة في تفاضل الفضاء العادي مفترض أن تزيد. طبعا هذه معلومة مهمة جدا. أنا الآن استكشف هذا العالم الغريب يسمى الستاندرد موديل. أنا أول مرة أدرس الستاندرد موديل بهذا العمق. فإذا نبدأ من اي جي تي سي 3 أو جي اي المتعلقة بالكيو سي دي. هذه طبعا متعلقة بالكيو سي دي، وأيضا مضروبة في المتعلقة بالكيو اي دي. هذه يجب أن تزيد كلما نقصت الأبعاد في التفاعل. كلما نقصت الأبعاد يجب أن تزيد هذه المعادلة، وهذا واضح. نجد الكيو سي دي مجموعة على هذه المعادلة، بالتالي إذا فعلنا الكيو سي دي إذن الأبعاد أصغر. هذا واضح جدا. لكن أنا أقصد في المعادلة الثانية اللي هي ابتداء من الجي دبليو والتي اي والدبليو ميو الدبليو اي ميو. هذه طبعا الميو تعتبر الاتجاهات في الفضاء الذي يخصنا نحن، أما الاي تعتبر 1 2 3 تعتبر الاتجاهات في الفضاء الذي يخص هذا التفاعل أو يخص هذا الانحلال، والذي تمثل بالمجالات المغناطيسية والتغيرات. جميل. الآن احنا نستكشف قليلا شيئا نربط معادلات على يوسف شيئا بشيئا في هذه المعادلة. طبعا الهايبر تشارج تي 3 زائد واي. التي 3 تعبر عن تدفقات المجال المغناطيسي بالنسبة للأبعاد الثلاثة كما ذكرنا، والواي ربما يكون تدفق مكان زماني. هذه معلومة جديدة أيضا. يعني يمكن أن نقول أن تي 3 تعبر عن تغيرات للمجال المغناطيسي بالنسبة للأبعاد الصغيرة هذه كما نراه نحن أن التي 3 تعبر عن التغيرات في المجال المغناطيسي المكانية في الأبعاد الصغيرة، زائد الواي التي تعبر في مجالات التغير في المجالات المغناطيسية في الزمان. وهذا يعيدنا للمعادلة أن الدي اكس أن الدي ار على الدي تي مفترض تتقارب كلما زاد الكتلة، وبالتالي نجد أن هذا الفرق بين التي 3 والواي كلما تعمقنا في التفاعل مفترض أن تتقارب مع بعضها البعض. إذا تقاربت سيكون تفسيرنا صح، إذا تباعدت سيكون لدينا تفسير آخر سنتعرف عليه.
We have fixed the gauge group, and we have also fixed part of the field content of the theory, namely we have fixed the gauge fields, which are the 4 gauge fields W and B. Now the next construction in gauge theory is to specify which matter fields there are. Matter fields by definition are all fields which are not the gauge fields. And here we have 2 kinds of matter fields, namely the Higgs field and the fermions. Let's start with the Higgs field, which is a so-called Higgs doublet. Doublet means doublet in the sense of the SU2 gauge group. We call it capital Phi. And let me be very explicit with specifying how the generators of the gauge group act. So, you know, these generators here must act in a way which is compatible with the commutational relations between them. For example, the generators TA must satisfy the SU2 commutation relations, which means T1 commutator with T2 is I times T3 and so on. This is just a number because it's a billion. This would have to satisfy the algebra corresponding to SU3. And but nevertheless, the exact values of the generators depend on which fields they act on. So I must now specify how the generators are defined if they act onto the Higgs field. And I will do that quite explicitly, at least for the first few cases. So if you act with a QCD generator TS on a Higgs field, what happens is you get 0. The generators, remember, they generate infinitesimal gauge transformations. So if the generator acts on phi and gives 0, it means that phi is invariant under QCD gauge transformations. That is the obvious and simple fact. It has nothing to do with QCD color charge, and therefore it stays whatever it is under a QCD gauge transformation. So the corresponding generator maps phi to 0. In other words, in the context of the Higgs field.
طبعا السبب في ذلك لأنه هو سبين زيرو، وسبين زيرو لا يتفاعل مع المجال المغناطيسي لأنه ليس لديه سبين، وبالتالي المجال المغناطيسي يكون هذا الضرب يساوي 0 مع الهيجز. وليس لديه سبين، ليس لديه orientation of the spin to z axis. الاورينتيشن يخبرنا بماذا؟ يخبرنا بأن مثلا نقول هناك يعني مثل مركز الثقل يتغير، مركز الثقل استقطاب مثلا ثنائي القطب، هكذا ثنائي القطب، يعني شيء من هذا القبيل. هذا ما يعبر لنا عن الاورينتيشن. وبما أنه ليس لديه اورينتيشن إذن هو لا يتفاعل مع المجال المغناطيسي. هذه معلومة في غاية الأهمية. لهذا نجد أن TA مضروب في الهيجز يساوي 0، خصوصا الدبلت، لأن الدبلت أو ربما يكون استطاع الفضاء الثنائي الأبعاد أن يخلق هذا الدبلت ليلغي بعضهم البعض.
The generator is just the number 0. What happens if we act with the SU2 generators onto the Higgs? This is a doublet, and that means in terms of SU2 the generators are given by 1/2 times the Pauli matrices. So this is now specifically sigma A over 2 multiplied with this Higgs doublet, and this is a 2-component object such that it makes sense to multiply the Pauli matrix 2 by 2 with this 2-component object.
طبعا المعلومة السابقة ستكون خاطئة تماما، لأنه ربما المعادلة الثانية لا يتفاعل مع هيجز، إنما يتفاعل مع WZ ربما، لأنه لديها سبين. ربما تكون كلامي صحيحا، ولكن لا يتفاعل مع الهيجز. هذا سيكون اختراق كبير جدا جدا في الاكتشافات، لأنه QCD يعبر عن مجال مغناطيسي، والإي دبليو عبارة عن مجال مغناطيسي. ما الذي يجعل المجال المغناطيسي يتفاعل مع هذا ولا يتفاعل مع هذا؟ إلا أن يكون هذه العبارة يكون خاطئة، أنه المجال المغناطيسي لا يتفاعل مع لا يتفاعل مع الهيجز، لكن يتفاعل مع WZ، وهذا معروف. أو هناك شيء آخر، الهيجز يعبر عن مجال كهربائي، وبالتالي عند QCD لا يوجد مجال كهربائي، إنما الخواص المغناطيسية تكون قوية جدا. عند الEW طبعا هي أشنع من الQCD، لأن أبعادها أقل، فبالتالي يجب أن تكون أيضا خواص مغناطيسية فقط. لكن اللي نرى هذا يعتمد على ظروف التفاعل، نحن محتاجين نعرف ظروف التفاعل. أنا طبعا دائما أقطع الفيديو وأتحدث هكذا حتى لا أنسى ما أقوله، وأحاول أن أتذكر شيئا في شيئا وأقارن أول بأول، لأنه إذا نسيت، إذا طولت الفيديو سأنسى ما قلته، وبالتالي لا أستطيع أن أقارن.
So you can say TA equals sigma A over 2 if you act on a Higgs field. So what about the hypercharge? Hypercharge can be fixed by thinking of this relationship. We want that the charge of the Higgs doublet is such that in the upper component we have charge +1, in the lower component we have charge 0, and therefore Y is basically the average of the two charges, so Y must be 1/2. 1/2 times the Higgs field, so in other words the hypercharge of the Higgs doublet is 1/2. And then if you go back into this relationship here, you see that in the upper doublet component T3 is +1/2, +1/2 gives 1 in the upper component, and in the lower component you have -1/2 +1/2 gives 0. Okay, and all of that can be Y is basically the average of the two charges, so Y must be 1/2. 1/2 times the Higgs field, so in other words the hypercharge of the Higgs doublet is 1/2. And then if you go back in hypercharge can be fixed by thinking of this relationship. We want that the charge of the Higgs doublet is such that in the upper component we have charge +1, in the lower component we have charge 0, and therefore Y is basically the average of the two charges, so Y must be 1/2. 1/2 times the Higgs field, so in other words the hypercharge of the Higgs doublet is 1/2. And then if you go back into this relationship here, you see that in the upper doublet component T3 is +1/2, +1/2 gives 1 in the upper component, and in the lower component you have -1/2 +1/2 gives 0. Okay, and all of that can be summarized by saying that the Higgs field is a so-called 1,2,1/2 representation of the gauge group. So you can summarize all these equations by this statement. 1 means singlet, so it is invariant under QCD gauge transformations. That corresponds to that equation. 2 means it is an SU2 doublet, therefore the generators are replaced by Pauli matrix over 2, corresponding to a doublet, and the hypercharge is 1/2. So this statement summarizes these three equations. Then let's go to the next quark left-handed doublet. Let's call it QLI. Where this I here corresponds to the color index. I runs from 1 to 3, corresponds to your QCD color charge. Okay, so you have an index. There are 3 quarks of the first generation of each flavor, corresponding to the 3 different colors. Then, so what happens if we act with the generators on it? First, strong interactions, TAS, acting on the quark left-handed. So now this acts in a non-trivial way because they do have color charge. And what color charge do they have? They are a so-called color triplet corresponding to the index I runs from 1 to 3. Therefore, we must replace the QCD generators by the triplet generators, which are the so-called Gell-Mann matrices, lambda A over 2. And what is the index structure? This matrix acts directly on this color index. So we would write this here as this overall with an index I. And the meaning is that you get here a Gell-Mann matrix, lambda A over 2, with index ij times QL index j summed over j, of course. So TS is now given by 1/2 times the Gell-Mann matrices, which are the so-called fundamental representation or triplet representation of SU3. Then, but we will not use that, of course, because we focus on electroweak physics. But then, what are the weak generators? TA acting on QLI. So in this sense, QL is a doublet. It consists of, let me write that here, it consists of ULI and DLI. So that is the structure. It is a doublet with 2 components, 2 entries. Each entry still has a color index, but anyway it has this 2 component structure, and the weak generators TA directly act onto this 2 component structure in the same way as for the Higgs. So we get sigma A over 2 times QL with the same index I. So the SU2 is blind to the color index I, but it transforms this doublet structure. So in simply put, we can again simply say the weak generators are replaced by 1/2 times the Pauli matrices. Then hypercharge. Hypercharge of the left-handed quark doublet is again such that the hypercharge corresponds to the average of the 2 electric charges. So here we have electric charge plus 2/3, here minus 1/3. The average is plus 1 over 6. So the hypercharge must be 1 over 6. And then we have again defined the action of all generators of the gauge group onto the quark doublet. And all of this can be summarized by saying it is a 3, 2, 1 over 6 representation of the gauge group. 3 stands for triplet, which immediately means TS becomes 1/2 Gell-Mann, and that means the same as before and this as well. And in this way, we have to go on to specify the entire.
طيب تعالوا معي تاني. تعالوا الهايبر تشارج. هايبر تشارج هذه هي Q يساوي T3 زائد Y. هايبر تشارج يعني تشارج. طيب الآن نحن الجبال قبل قليل ذكرنا أنه في الكيو اي دي في الهيجز وجدنا أنه الهايبر تشارج هي سيجما على 2 زائد نص. هنا الواي بنص وهذه سيجما على 2 تي 3 سيجما على 2. وهنا في الكلر وجدنا انه ايضا سيجما على 2، لكن الواي اصبحت 1/6 من نص اصبحت 1/6. ما الذي جعلها تنقص من الانتقال الى الكيو اي دي او الالكترويك؟ هنا قال ماذا؟ من الانتقال من تفاعل الميون الى تفاعل الكوارك. ما الذي جعلها تنقص؟ تعالوا نوريكم من الذي جعلها تنقص. ما جعلها تنقص هو هذه المعادلة نسبة لوجود الفي السرعة، وجود الفي السرعة. هذه طبعا ليس اكس، انما هي مضروب، هي كروس. سأعدلها انا حتى لا تصل لي مشكلة. فالفي هي التي عدلت هذا. طيب كيف تعدلها الفي كيف تعدل هذه نسبة؟ لأنه مع نقصان الأبعاد زادت الكتلة أو زادت الطاقة، نقصت المسافة بين أو الفرق بين إكس دي آر والدي تي، بما أن المسافة بين الدي آر والدي تي تقاربت، هذه يعني السرعة زادت. إذن في حالة الكار في حالة الكوارك مسافات صغيرة، في حالة الليبتونات مسافات كبيرة أو طاقات. دعنا نقول بالطاقة، الأفضل نقول بالطاقة. في حالة الليبتونات طاقات أقل، وفي حالة الكوارك طاقات عالية، وبالتالي تنقص المسافات، وهذا ما يجعل الهايبر تشارج تنقص. سيجما على 2 سيجما على 2 1/6. تعالوا نشوف الجلمان. رجعني شغف لأشوف الجلمان أو الجلمان اللامدا. هنا تصوير سيء جدا جدا، ما مساعدني نهائي. في حالة الكيو سي دي التي اي تمثل بالجلمان. نعم، لامدا اي على 2. تعالوا شوف لامدا اي على 2 ماذا تعني. جلمان هل تنقص أم تزيد؟ يعني نتكلم على الكيو سي دي الآن، يعني طاقات عليا طاقات عالية. تعالوا نبحث عن الإنترنت. طيب جلمان ماتريسيس. واحد ليست نصف. عبارة عن واحد. جميل، هو ليس نصف. إذا في حالة الكيو سي دي نجد أن الجلمان أكبر من الباولي ماتريسيس، لكن ستكون الأمر الثاني في الهايبر تشارج قال كم؟ لا أعتقد أنه ذكر شيء. وغاية هو الكيو سي دي ما هو تعتبر الكلر عبارة عن 1/6. تعتبر الكلر كوارك، يعتبر الكلر 1/6. يعني في كيو سي دي وفي الكوارك في الكيو اي دي، ولا أقصد الاي دبليو كوارك هي كلها 1/6. وبالتالي نجد أن واي التي تمثل واي قال ماذا تمثل الواي؟ نعتقد أن الواي هو السبب الذي يجعل هذه المعادلة تنقص، لأن ديك عبارة عن ماتريس، عبارة عن ماتريس التي اي عبارة عن ماتريس، لكن الواي هي السبب في نقصان الشحنة الهايبر تشارج، وهي التي تتعلق بالسرعة. طيب تعال نواصل.
Just clean the blackboard. Okay, where are we? So we have now the Higgs doublet, quark doublet. Let us go on with the lepton doublet.
جميل، تعال نشوف الليبتون.
Let's call it capital L subscript L. This L stands for left-handed, of course, which consists of the left-handed electron neutrino and the left-handed electron. And it has the following quantum numbers, namely it is invariant under QCD color gauge transformation, so TS again is 0. It is an SU2 doublet, so TA is replaced by sigma A over 2, and it has hypercharge -1/2 because -1/2 is the average of the two electric charges, and so it can be written as a 1,2, -1/2 representation of the standard.
جميل، أكبر من الكيو سي دي، أكبر من الكيو سي دي. إذا إحنا نظريتنا حتى الآن ماشية تمام، نظرية تمام. معنا هذا يعني أن المجالات المغناطيسية هي الفعالة. أنا أحاول أن أثبت أنها المجالات المغناطيسية، كل ما في الأمر.
Then we have quark singlets. On the one hand, URI. So this is a right-handed up quark electroweak singlet. So it is a color triplet, TS, acting on this. I is S4 for the quark doublet, given by Bellman matrices, IJ, URJ, the same as before. But now, for the first time, we have something which is an electroweak singlet. That means the TA generators for SU2, they leave this invariant, which means the generators map it to 0, because the singlet is invariant under SU2 gauge transformations. And hypercharge, according to that formula which we have over there, TA is now 0, therefore the hypercharge is equal to the electric charge, which is here 2/3. And similarly,
انظر انها زادت مرة اخرى، يعني زادت حتى من الكيو سي دي، وزادت حتى من الالكترويك. في حالة الليبتونات زادت ايضا الواي، زادت مرة اخرى. بالتالي نجد ان ما نقوله عن الطاقات العليا وعن المجالات المغناطيسية صحيح.
For the right-handed down quark singlets, okay, or let me just say it like this. So this is now a 3,1, 2/3 representation. Okay. And now for all the other ones, I can just use the shorthand notation, namely DRI in a similar way is also a 3,1, -1/3 representation, which means that it transforms in the same way under color, it transforms in the same way under SU2, but it has a different electric charge and therefore a different hypercharge, so that is the only difference. And then the lepton singlet. Which I call RI in a similar way is also a 3,1, -1/3 representation, which means that it transforms in the same way under color, it transforms in the same way under SU2, but it has a different electric charge and therefore a different hypercharge, so that is the only difference. And then the lepton singlet. Which I call small ER. This is which representation? So can anybody guess or tell us what would be the representation of the electron right-handed singlet? So what is its color representation? How would it transform under color SU3 gauge transformations? 1, in the same way as all the other leptons. So 1. How does it transform under SU2 gauge transformations? In the same way as what? There's the quark singlet, so it has here a 1, so the TAs are 0. And then, like for the quark singlets, hypercharge equals electric charge, which is -1. So here, that is what we do. And so, in the end, you only need to know these sort of statements, which is exactly what you would say in words. In words, you would simply say, we have a right-handed electron singlet under SU2 with electric charge -1, and then you know this, and then you can reconstruct how all the generators act. Because nobody would need to remember these equations or learn them by heart. You must know that these equations automatically are a consequence if you specify this data. Okay, and so then we have specified the full field content of the standard model. And the gauge invariance is then the requirement that the Lagrangian should be invariant under the corresponding gauge transformations. So you have discussed non-abelian gauge theories already in this lecture at the beginning of the semester, and also in the parallel quantum field theory 2 lecture we have discussed abelian and non-abelian gauge theories. And so whenever you know what is the gauge group and what are the matter fields, you automatically know exactly how the gauge transformations must look like. So I do not write them down because they can be reconstructed straightforwardly from all the information on the blackboard, and then we also know what it means to say that the Lagrangian should be invariant. So no need to waste time in writing down the corresponding equations because they are simply contained in that information. Let us go on. The next step is the Lagrangian. And as I said, the standard model is really defined by the field content and by the symmetry content, and therefore the Lagrangian is a consequence of what is written on the blackboard and doesn't need to be defined separately. So L is defined as the most general local relativistic renormalizable Lagrangian, which is invariant under the above gauge transformations. That is the definition. And therefore it just remains to work out what is the most general Lagrangian in agreement with this. And generally speaking, we know from the general discussion of gauge theories, how does a general gauge invariant Lagrangian look like? A general gauge invariant Lagrangian looks like this. that it might depend on the field strength tensors F mu nu corresponding to all the gauge fields because they are gauge covariant objects. In addition, it might depend on covariant derivatives, but it must not depend on ordinary derivatives separately. It must only depend on covariant derivatives, and then it might depend on all the meta fields. And that means, of course, it can depend on covariant derivatives of the meta fields, but it cannot depend on ordinary derivatives of the meta fields. And then I do not copy again that it must be local and relativistic. That is so, let's say, clear that let's not repeat this. But what does it mean that the Lagrangian is renormalizable? It means that in the Lagrangian there must at most appear terms composed out of those fields and derivatives which are of dimension 4 or less. So this gives rise to a sum of operators times coefficients. Operators mean any combinations of fields and derivatives, and each operator which can appear in the Lagrangian in the sum must have dimension 4 or less. So with at most dimension equal or smaller than 4 terms. Because everything else would then violate renormalizability. Okay, and with that in mind, we can write down the Lagrangian. I am sure that all of you know the standard model Lagrangian from the T-shirts and the CERN cups and so on. And so basically we just write it down and comment a little bit on the individual terms, but you will see that they all correspond to that structure. As you know from the cup and the T-shirt and so on, the Lagrangian has 4 lines, which is a very neat way to split up the Lagrangian into the 4 different contributions from the gauge bosons, from the kinetic terms of the meta fields, from the Higgs potential, and from the Higgs fermion interaction, the so-called Yukawa interactions. And we will use basically the same split into the respective terms. So let us begin with the kinetic terms. There are gauge kinetic terms. First of all, L gauge, which is the sum of all the squares of the field strength tensors corresponding to an abelian or non-abelian gauge theory. So I will again here for the last time maybe write including QCD, EA mu nu times EA mu nu, which would be the field strength tensor corresponding to the gluons, which we will drop afterwards. Minus 1 over 4 WA mu nu, WA mu nu, minus 1 over 4 B mu nu, where these correspond to the field strength tensors corresponding to SU2 and U1. And let me just say as an example, you can get the field strength tensor from commutators of covariant derivatives. So for example, WA mu nu contracted with the SU2 generators TA is given by 1 divided by I times the gauge coupling TW times the commutator of 2 covariant derivatives, d mu d nu, and from that only the SU2 part. That gives you the field strength tensor corresponding to SU2. And then you can extract the individual WAs by taking some traces with respect to other TEs and so on. So this defines implicitly all the WAs. The gluon field strength tensor is defined in the same way, and the B mu is defined in the same way. And for the non-abelian cases, you have non-trivial commutators between generators, and then here on the right-hand side you have non-linear terms in the actual field. But for the abelian case, where the generators commute, you only have linear terms on the right-hand side. And so for the non-abelian case, you get self-interactions between the gauge bosons from those terms. From the abelian case, you do not get self-interactions between gauge bosons. And as we already discussed, we need self-interactions because of the interaction of the W with the photon. So that is contained in here. Okay, these are the gauge kinetic terms. Then we have the meta-kinetic terms, which are first of all covariant derivative of the Higgs doublet squared, because that is the correct Lorentz invariant kinetic term for a scalar field, but gauge invariant, so we use the gauge covariant derivative. Then we have the same for the fermions. Let's start with the quark. QL I bar times I gamma mu d mu QL I. That would be the correct kinetic term for a fermion, and it is also Lorentz and gauge invariant. And then we have similar terms for all the other fermions. And that describes the kinetic terms of all the meta fields, and because of the gauge covariant derivative, at the same time this describes, of course, the interaction between the meta fields and all the gauge bosons. For example, it describes what we had here somewhere on the blackboard, these interactions, photon, FF or Z boson to two fermions, W to two fermions. This is described by those terms in the Lagrangian. Then the next is the Higgs potential. So we write L Higgs potential is equal to minus V of phi. So by convention, of course, the potential appears with a minus sign in the Lagrangian. And let us directly specify the value of the potential. And the conventions I want to use are minus mu square times phi absolute value square plus lambda times phi absolute value to the fourth power. And so in this way we make explicit here the Mexican head structure of the Higgs potential. If mu square is positive, then we have here a negative term, and we get this typical Mexican head or wine bottle potential. And for lambda, there are also many different conventions available. Some people put here a lambda, some people put lambda over 2, some people put lambda over 4. And this convention that I am using here is the one which is typically used, for example, by De Grassi et al., who discussed the vacuum stability of the standard model, which is an extremely important application of the Higgs potential, where they calculate higher order corrections to the Higgs potential and ask whether, including higher order corrections, it still remains a Mexican head or whether it changes its shape. And so since these are very important studies of the Higgs potential, I use here their convention for lambda. But other conventions are equally possible. So gauge kinetic, metakinetic, Higgs potential term, and the last remaining one are the Yukawa interactions. So L Yukawa is the following: minus Yukawa coupling for the electron. So this letter here is a small e, YE for electron. Then capital LL bar phi ER. Okay, so what you see here is the Higgs doublet, which is an SU2 doublet. Then the lepton doublet, left-handed, barred, such that in combination we get Hermitian adjoint doublet times a normal doublet, and the product of the two gives something which is obviously SU2 invariant, because the doublet structure is compensating. And then we have here a product between two fermions, a left-handed fermion barred times a right-handed fermion And that is a non-trivial Lorentz invariant expression how you can multiply two fermion fields. So the fermion structure, Lorentz structure is okay. SU2 structure is okay because Barth doublet times singlet is SU2 invariant. And you can check the hypercharges. That has hypercharge -1, hypercharge +1/2, hypercharge -1/2, but complex conjugated. So the hypercharges add up to 0, and so it is also invariant under the hypercharge gauge transformations. So this term makes sense from the point of view of Lorentz invariance, and it is fully gauge invariant. And it corresponds to an interaction of two leptons and the Higgs. Let's go on. We have also the same for the down quark, YD, times the quark doublet, QLI for each color, times the Higgs doublet, times DRI. And we simply sum over the colors. The Higgs has no color, therefore we trivially sum over the three colors of this. And again, we have anti-doublet times doublet is SU2 invariant. The hypercharges are here -1/6, +1/2, -1/3 gives 0. So it's fully gauge invariant, and it makes sense from the Lorentz invariance point of view. And as you know, what is the output or outcome of these terms? The masses of the electrons and quarks, right? You know that, don't you? Okay. So what is missing is the up quark. So how does it look like for the up quark? Let's first write down something which looks like that. Let's simply write it and now study it, but maybe with a bar. So this also makes sense from the Lorentz invariance and spinor point of view. But what about gauge invariance? Now SU2 anti-doublet times doublet gives a singlet. That is okay, but what about hypercharges? They cannot add up to 0 because this is the same, that is different, and so the hypercharges add up to 0 here, but here they don't, because that is just has the wrong hypercharge. So how can we obtain a term which gives rise to masses for the up quarks? Not in this way. So we need another way. And if you just look blindly, then the hypercharges here are -1/6 +2/3 give +1/2. If we do that, then the hypercharges add up to 0. But then we have anti-doublet times anti-doublet. That is not obviously gauge invariant, and so under SU2. So we need to do something, and what we can do is the following. Let us exhibit the individual SU2 components. So let's put here index A, index B. AB stands for the two components of the SU2 doublets, and let's multiply it with the epsilon tensor epsilon AB, where epsilon AB is antisymmetric, equal to minus epsilon EA, epsilon 1, 2 is equal to +1. So that is the epsilon tensor, and the A stands for the SU2 doublet components. Then the third term is actually also gauge invariant, and we have to prove that, of course. Good, but that is first of all the Lagrangian, and so the sum of all the terms, this electroweak standard model Lagrangian, is equal to the gauge kinetic terms plus the metakinetic terms plus the Higgs potential plus the Yukawa sector. These are the four lines of the electroweak Lagrangian. So maybe let me end the lecture by a few comments. So first of all, let us check the gauge invariance of these terms. Let's first say all terms are obviously gauge invariant except for this last one. Okay, maybe for some the last term is also obvious, but it is less obvious than for all the other ones. Let us first check, is it true that all the other terms are obviously gauge invariant? So if you have a covariant derivative, the thing transforms as the original object without the derivative. And so therefore it is clear that this is gauge invariant because of the phi square. This is gauge invariant because of the Q dagger Q. So all the gauge transformations always obviously drop out of those terms. The gauge kinetic terms are of course gauge invariant because of the construction of non-abelian gauge theories. That was non-trivial, but we constructed it, and so therefore this is just knowledge. And this is obviously gauge invariant because of the absolute value square. This is gauge invariant as we discussed, and so the only non-obvious term which remains to be discussed is the last one. Therefore, is it true that all the other terms are obviously gauge invariant? So if you have a covariant derivative, the thing transforms as the original object without the derivative, and so therefore it is clear that this is gauge invariant because of the phi square. This is gauge invariant because of the Q dagger Q. So all the gauge transformations always obviously drop out of those terms. The gauge kinetic terms are of course gauge invariant because of the construction of non-abelian gauge theories. That was non-trivial, but we constructed it, and so therefore this is just knowledge. And this is obviously gauge invariant because of the absolute value square. This is gauge invariant as we discussed, and so the only non-obvious term which remains to be discussed is the last one. Therefore, let us discuss it. Let us discuss how it transforms under a gauge transformation. And the only thing that we need to check is SU2, because it's obviously invariant under color, QCD, and it's also obviously invariant under hypercharge, because that is how it was constructed. Let us only check SU2. So then we write down only the SU2 part, namely this QA times phi B dagger. So that is, you take either the upper or the lower component of the doublet and dagger it. And here you take either the upper or the lower component of the doublet and bar it. And then you multiply with epsilon and sum over A and B. So now you do an SU2 L gauge transformation. Now what happens? So the epsilon is just a numerical prefactor that doesn't do anything, but the Q transforms, namely Q transforms by an SU2 matrix. And so I will now not use the infinitesimal form, but I will use the finite gauge transformations where I just know that the doublet is multiplied with an SU2 matrix. So that is now our SU2 matrix. It's a unitary 2x2 matrix with determinant 1. And that is multiplied with our doublet. And after multiplying the matrix with the doublet, I extract the component A. So I can write this as U A prime times Q L I A prime. That combination here gives me the gauge transformed QLA. And all of that is barred. Then the Higgs field. So the Higgs doublet, first of all, transforms also with the same SU2 matrix, namely it transforms into Q U B B prime times phi B prime. That is simply the transformation of the field phi B. And now all of that is daggered, because we need here phi b dagger. So that is the gauge transformation of phi b dagger. Yep. So that is the following, epsilon AB. And so let us exhibit the appearance of the SU2 matrix. So here we have the bar. Bar means is an operation for spinors which involves complex conjugation. So this is a numerical prefactor in front of the spinor. So for the numerical prefactor, the only thing that the bar is doing is complex conjugation. So we get here U star, matrix element AA prime, and then QA prime LI bar. And here, that is a numerical prefactor for any index BB prime. So the dagger just means complex conjugation again, U star BB prime, and then times phi B prime dagger. And now I've just rewritten the term, and what do you discover? You discover here a combination of mathematical objects, namely an antisymmetric tensor times a matrix, twice written in this way. And I hope you have seen this construction before in mathematics. Namely, what is this? That is the definition of a determinant of a matrix, isn't it? So that is by definition equal to epsilon A prime B prime times the determinant of the matrix U star. So for example, if you put A prime equal to 1 and B prime equal to 2, so you have here epsilon 1, 2 is 1, okay, 1, 2. Then you see here A prime becomes 1, B prime becomes 2. Then you see here epsilon AB times U A1 to B2. And then what the product gives you is the product U11 times U22 minus U12 times U21. That is exactly the determinant. So and this works also for matrices which are not 2 by 2. It works for n by n matrices. You would have to put here an antisymmetric tensor with n indices, and here n factors of your matrix with that sort of structure, and then you always get the determinant of the matrix times the remaining epsilon. So that is a general mathematical definition of a determinant. What is the determinant of U star? In our case, where U star is an SU2 matrix. It is 1. It is 1, and therefore the thing is gauge invariant. That is the reason. And we have here. And now if you look at it, you literally see on the right-hand side of the equation the identical object as on the left-hand side of the equation, just the index got relabeled A to A prime, B to B prime, but otherwise it is identical. And so we have proven the gauge invariance of this object, and it is related to the fact that our matrices have determinant 1, so SU2. And okay, as a side remark, maybe you discussed it also with Peter in the other part of the lecture. So you can generally do this also with SUN gauge groups. If you have an SUN gauge group, you can always write down such an expression where you have an epsilon tensor with n indices, and here a product of n objects in the fundamental representation. And then this thing would be gauge invariant. So in SU2, it is just a two-dimensional epsilon tensor and a product of two doublets. That it gives something gauge invariant. The counterpart in QCD would be you have here an epsilon with 3 indices and a product of 3 quark fields which are color triplets. So 3 color triplets multiplied with an epsilon tensor gives something color gauge invariant. And that has a physical interpretation, namely baryons. Baryons make use of this. Baryons are gauge invariant objects which are composed of 3 quark fields, each in the fundamental representation of SU3, and you can connect them using the epsilon tensor in this way. And therefore, the generalization would be that in every SUN gauge group you have 2 ways to generate gauge invariant combinations of your fundamental objects. One way is the obvious one, a barred object times an unbarred object is gauge invariant. In the QCD case, that would correspond to mesons, which are composed of 1 antiquark and 1 quark, which directly is color gauge invariant. But in all these SUN gauge groups, you have also this epsilon times n objects, where n stands for SUN. And that corresponds to baryons in QCD. So for any SUN gauge group, you have something analog to baryons, which would always consist of n fundamental objects placed next to each other and combined with an epsilon tensor. And in SU2, it just happens that the baryons are composed of 2 objects like the mesons. So this would be mesonic structure. That would be baryonic structure in the language of QCD. Okay, but anyway, that proves that all terms are gauge invariant. The next note is, of course, that is not obvious, but you can check it and you can prove that there is no other gauge invariant term with dimension less or equal to 4. So we have really collected all gauge invariant terms. Maybe as a further remark, except the so-called theta QCD term, which is a total derivative. So one could add terms which are gauge invariant but which are total derivatives, and they are of interest for non-perturbative physics, but they can be neglected here. So these are important and kind of obvious remarks. Let me also make a few further remarks. So first of all, there is no explicit fermion mass term. Because mass terms for fermions would look like this. For example, a left-handed electron bar times a right-handed electron. This is a mass term for an electron field, but this is not gauge invariant. And the same is true for all other possible mass terms for all fermions in the standard model. We cannot write down gauge invariant mass terms. And that is only true because of the weak interactions. This term is perfectly gauge invariant under QCD, and also all the quark mass terms are perfectly gauge invariant under QCD, and also under QED gauge transformations. This is also gauge invariant, but the weak interactions make it non-gauge invariant. So that is very important. So all the fermion masses of the standard model must be generated in a different way, not by explicit mass terms, but as you know, from coupling to the Higgs vacuum expectation value. And this is something which is not true for all particles in all theories. It's a specific property of the standard model and the specific quarks and leptons which we want to describe. For them, such explicit mass terms are not gauge invariant. Then another remark, all terms in the Lagrangian are exactly dimension equal to 4. So we had the requirement 4 or less, but actually all terms are exactly equal to dimension 4 except 1. So by dimension 4, I mean, for example, this term, the Higgs field has dimension 1, the derivative has dimension 1, so the product here has dimension 4, and the prefect 4 is 1 is dimensionless. So this is the dimension 4 term. Similar, a work field has dimension 3/2. Derivative has dimension 1. The product has dimension 4, and so on. You can go through all the terms. All of them have dimension 4. Here again, fermion plus scalar, dimension 4. There is only one single term in the entire Lagrangian which doesn't have dimension 4, and it also doesn't have dimension 3, but it has dimension 2, and that is the Higgs mass term, mu squared, the mu squared term. So this is the only term which generates a dimension-full scale in the standard model. Without that term, the entire Lagrangian would be scale invariant and would not contain any thing which defines a unit of energy or unit of length or mass. That is interesting, and maybe now the time is up. That is a little bit unfortunate, but we have another lecture in the afternoon, so then I can add our first or maybe second miracle of the standard model. Let's do that at the beginning of the next lecture. Okay, so see you in the afternoon.